last type of bonding model that we talk about here is molecular orbital theory. Now, it's worth drawing to your attention that molecular orbital theory is super complex. It's for this reason that we really don't see it used all that frequently in organic chemistry. When we're talking about organic chemistry, we are typically looking at valence bond theory. But here we're going to cover some basics to help you out. So molecular orbital theory is the most complex, but it does something really important. It considers something called an antibonding orbital, as well as a bonding orbital. Now, the reason why the antibonding is important is because it does explain a lot of observed behavior in organic chemistry. Now, we'll think about the simplest example, which is hydrogen, or H2. Now, if I'm to think about H2, each hydrogen atom has a 1s orbital, and it each brings one electron like so. When I think about molecular orbital depiction, I think about a bonding interaction, and a bonding interaction is one which we consider in phase. So you'll notice I've taken the two s orbitals, they're both spheres like so, and I've drawn them in the same phase. Nothing is filled for no reason other than the fact that I'm lazy. If I wanted to fill them all in, that would have been fine too, as long as the two phases of each hydrogen atom are the same phase. This is considered a productive or constructive bond. These are the two wave patterns of each of the orbitals interacting in a constructive way to make a bond. The antibond looks like so. It's out of phase, and the reason why we call it an antibond is because it's out of phase. If I was to put electrons up here, this would be a bad thing. This would hurt the amount of bonding. You'll notice that it's higher energy because, of course, to have an antibonding orbital is higher energy than to have a bonding orbital. So molecular orbital depiction takes H2 and draws it as the sigma and sigma star. The star annotation being that for the antibonding orbital. Let's look at a slightly more complex example. So this more complicated example is ethene. Again, it has a sigma bond between the carbons and a pi bond between the carbons. Now we know that the sigma bond between the two carbons could be some sort of hybrid, and the pi bond requires p orbitals. But each of these bonds can be shown with bonding and anti-bonding combinations. Let's draw them in. Let's start with the sigma bond. Here we should have these hybrid orbitals interacting in an in-phase way. You'll notice I have them pointed at each other and I have the big in-phase lobes facing each other. The antibonding orbital, of course, will be out of phase, and so it'll look something like this, where we have the two big lobes pointing at each other, but now they are out of phase. One is shaded and one is not. It doesn't matter that I picked the left-hand side to be shaded. It could have been the other. What matters is they're out of phase. The pi bond requires p orbitals, like so. The pi bond should be in phase, and the antibond should be out of phase, like so, where we have the two different lobes shaded in a different way. So this just shows you the sigma star and the pi star of ethene. Since molecular orbital theory is so complicated, it tends to not be used a lot in organic chemistry. Having a superficial understanding, being able to draw what I just drew, will be more than enough to get you through your courses.